Anyway, so we will continue from lecture 1 on to lecture 2, which is in the middle. Quick review. We figured that we can write the screw simply by inspection. Okay, and well, you have to know a little bit of trigonometry, a little bit of geometry, make a neat figure, and then you can pretty much write down all the screws. Okay. Now once you have written it, you then come down and you can write the Jacobian. Okay, I will repeat again. This is not in the base coordinates. Okay, it is in a coordinate system which is fixed on the fourth link. Now, so idea is that you can go ahead and count. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 zeros, 19 zeros. 19 out of 36 elements, 19 are zeros. Right? There are several of them which are just ones, and then there is nice terms like only H and things like that sitting around. So determinant of this is obviously fairly easy to compute. Okay. How do you find the determinant of this? So you could start by, well, this is a very nice row to start from, a column to start from. So if you pick this, there is only a one entry here, right? So you could pretty much knock this off and you knock off these elements. Okay. So is there anything else equally nice looking around? Perhaps not, but there are these two interesting columns which have two entries. This has only two entries, so on and so forth. This one has three entries, so this is not so useful. So we should then concentrate either on this one or on this one. Okay. So then I will have to evaluate only two more cofactor matrices. Now this one is very interesting. This, if you look at this term, this term, this term, this term, this 2 by 2 matrix, what is the determinant of this 2 by 2 matrix? So this minus GC4 multiplies with this, so you get a term of minus G C4S4. You get from this, you get plus G C4S4, so that cancels out. So only other term is FG S34 C4 minus, and from this you get plus FG C34 S4. So that is equal to S3, which is the term which is here, FG S3. Okay. So this also simplifies very nicely. Then this term FC2 plus GC23, as you can see, is this term, and this HC234 comes with this H multiplied with this C234. Okay. So eventually the determinant comes out to be a very nice and compact term, and simply because you have so many ones and zeros all over the place. Okay. And this term turns out to be equal to x15, where x15 the x coordinate of O5 in this x1, y1, z1. Now this has implications, this being equal to x15, which essentially means that if you are multiplying out the matrices 1, 0, 2, 1 in order, then you can easily find out what this term x15 is. Right? Is the x coordinate O5 in x1, y1, z1. You don't have to work very hard to find out what the term is. Okay, it's already, so if you have a DH representation of the robot, you can quickly calculate the determinant without physically evaluating the determinant of this matrix, which in general would have been very large. Okay. So are these concepts reasonably okay? So I can do it quickly, and when I eventually calculate the term, I am going to use the DH parameters and those matrices. But this tells me that I just need to evaluate this parameter x15 and I am in business. I do not have to do the rest. And remember that to do my forward kinematics, I will anyway have to multiply those matrices out. So it's not too much additional work. I am just using my knowledge of robotics to combine these things together. Now, I will just show you this manipulator again. So the question now comes is, sorry, I jumped ahead. So we had said that when the determinant becomes equal to 0, then the Jacobian cannot be inverted, right? It cannot be inverted. So we've said the manipulator loses some degrees of freedom. So there are three conditions here. Obviously f and g cannot become 0 because they are physical link lengths. It's only S3, C5 and X15 which can become equal to 0. Okay. So what is the situation here? Sorry. So when this angle becomes equal to 0, no, it is S5, C3. So when this becomes 90 degrees, C5, S3. No, when this is 0. So if this angle is 0, what happens? What degree of freedom does the manipulator lose? Okay, we will get to that. What happens when this C5, that means this is turned 90 degrees, so that this is looking this way, what happens in that case? That is easier because then you do not have anything which gives you a twist about in the radially outside direction. So that rotation goes away, right. So that is easy. Third one is X150, that means this link turns up somewhere on this axis. So you have bend it around so that this link turns up somewhere on this axis. Okay. So if that happens, you can quickly figure out that you cannot move the manipulator temporarily along the y1 direction. Okay. So these are physical conditions which you can actually identify with the manipulator, that this is what is happening to it, if you have an analytical formulation like this. Okay. So for each of these things, 1 degree of freedom is lost. So you can just verify that for S3 equal to 0, you lose translation along x1 axis, C5 rotation about y1 axis, and x15 translation along y1 axis is lost. Okay. And we have discussed that these positions are called singularities or special conditions, because it's not always, it's just the full range of angles, only it happens couple of cases. For a large range of x15 values for one particular set, you get this problem with a manipulator. And well, if you want a manipulator which does not have such singularities, the full workspace is available to you to do anything you want, then you have to usually go in for, if your workspace is 6 degrees of freedom, you have to go in for 7 or 8 degrees of freedom manipulators. Okay. And there are situations like this. Anyway, so we will discuss, have a look at these later. So the other question which you should have asked me is, understand this, but am I getting this because I'm evaluating Jacobian in the fourth coordinate system? Because when we did the planar one, we just evaluated in the base coordinate system. And finally, when I want to invert the Jacobian, I want to invert a Jacobian about the base coordinate system. So does it matter if I find the Jacobian in the fourth coordinate system, so on and so forth? Okay. It turns out it does not. Why? Because determinant is a intrinsic matrix property, so which is invariant on coordinate transformations. Value of the determinant, eigenvalues, eigenvectors, they are invariant. Eigenvalues, not eigenvectors. They are invariant with coordinate transformations. So it does not matter, and we can use this, and we do not need to analyze the singularities about a base coordinate system. So to find the inverse, how do you find the inverse? We have to evaluate cofactors. You know what is cofactors, right? Okay. Evaluate cofactors and you divide by the determinant, the standard method. And we saw that the determinant itself was not very complicated. It's a fairly simple set of terms. So each cofactor is bound to be simpler than that. Yes, no? Bound to be simpler. And it will not have contain elements with too many terms. We are fairly clear about it. And in this case, so we started with, when we wrote the original Jacobian, they were just screws written in column order. Okay, so LMN PQR, P star, Q star, R star. After you find the inverse, they will become screws, okay, in the row order, but they will go P star, Q star, R star, L, M and N. Okay. So what are the two orders that I talked about? Ray and axis, right? So it goes into the other order. Okay, this is just, you don't need it to actually use it, but this is information which you should know, because if you want to do further messing around with it. And so this is what it looks like. Is it? So the number of zeros has reduced in this expression. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, only 12 zeros, down from 19. But each term is fairly tractable. It's not so bad. And these terms, which you see down there, x14, fc2, so these kind of terms, so these are all the coordinate of the origin of the first coordinate system expressed in a frame attached to the fourth coordinate system. There is x14. Similarly, z41 is coordinate of the z coordinate of the fourth coordinate system expressed in the first coordinate system. So these are all terms which you can neatly evaluate from the DH parameters if you want, or you can directly calculate them. Obviously, it's not terribly bad. FC2, which is not very bad terms. Now this is the inverse in the fourth frame. So now we have to solve what is called the inverse velocity problem, is what we had been talking about. Okay. So we are now looking at trying to compute the actuator angular speeds omega 1 to omega 6 to achieve the end effector specific requirements. Okay. Now to do that, what we do is we have to evaluate this kind of expression. So what we do is we take LMN P star Q star R star, which is the desired instantaneous motion in the base or the zeroth coordinate system. we then add the transformation from 0 to 4, 0 coordinate system to the 4th coordinate system, multiply by the Jacobian inverse, and you get the omegas. Now these omegas, whether you calculate in the 4th system, 1st system, it is the same, because again it's a physical property. How fast are the motors moving, or do they need to move? So it does not matter. So this is quite neat, and you can also write down the transformation matrix in a fairly compact form without a great amount of this thing. Well, this is always 0, but these are also very compact, not very large terms, and you have to apply this only to one screw. So you don't have to multiply all 6 rows of a matrix or do it large number of times. So only once. So overall, this process is much more efficient than trying to find out the Jacobian of the manipulator by some other means and then trying to and then you find the Jacobian, then you invert it. So you could have gone by the DH thing using the method which I showed, not the definition method, but some other method, by the second method, numerical method that I had talked about. You could have done it that way, except that this is likely to be more compact and more computationally efficient. So is this clear? So oh, I seem to have jumped ahead. And so just to review, you have to apply it only one column once in this process, not a large computational overhead. Terms like x14 in the inverse Jacobian matrix and the transformation matrix, they can be calculated directly, okay, from the DH matrices. And second thing is, having symbolic expressions gives the overall picture that is difficult to assess numerically. So for example, you know right now that if your sin theta 3 is going to 0, you are going to lose out on this motion. So even if you are not using this explicitly, you have this knowledge about the manipulator. If you are programming it in an industrial environment, you will naturally want to move away from these kind of situations, right? You will not want this manipulator to fold back and come pretty close to its own base, because you anticipate that you lose a local degree of freedom, and if you have to move then you will have problems. There are other things which you can do. If you know the magnitude of the determinant, that tells you, it's called a condition number. So that tells you how agile the manipulator is at a location. So the larger number, so the smaller the number, the more singular it becomes. That means it's tending to lose a degree of freedom. The larger the number, it means that it is currently able to move in all directions better and better. So it goes the other way around also. So knowing the determinant helps. And the final thing which I want to tell you is that you can do similar formulations for quite a lot of robots and for most industrial manipulators by setting up somewhere around the wrist. Okay, so somewhere 4th, 5th coordinate system works out pretty much okay. 3rd, 4th, 5th, and you have to just mess around with the orientation of the coordinate system. Doesn't matter. You will be landing along something or the other, and you can pretty much work it out this way. Okay. So any questions? No. It's a good class. Or I am a good teacher, explain and everything goes in first shot. Did any of you look up the infinitesimal screw notes? Not yet. You should look, like I told you, it seems like there's whole of 2 months, barring 1 week in the middle before the second minor comes. So better start catching up. If you wait till then, you'll be in trouble. Okay. So we don't have the Friday class, so I want to show you So you can see the phenomenal speed of this, right? It's right, grabbing and moving, grabbing and moving it, and you can see the structure is, so now it is tired, it is flexing itself a little, right, and then it gets back to work, okay, at a phenomenal speed. And if you watch carefully, so the motors for this are located here. This is one motor, this is a motor, okay, and is connected by these arms, okay, and locally at the wrist it has got some orientation capability, right. So this is called a delta manipulator. So it's a parallel manipulator, okay. So this no. Let's look at the next one.
So why do you need parallel manipulators? Why does not one arm suffice? Why do you need?
Look at the speed of this. What you have seen in the lab.
Yeah. Okay. So this for the speed, right?
Yeah. Because see, you can put these large motors at the base. Look at this one. Okay. This is an advertisement by a company called Moog. So this has translating things at the base. So these are translating axis, and then the top moves with 6 degrees of freedom. Then let's look at another one. So this is again what is called a GOF platform. So the reason you want to put this, because you have the platform and your actuators are located away from it. So this other robot, they carry their motors around. Okay, the first carries all the other 5. The second carries 4 motors. So here you can see these huge motors which are sitting at the base, where you can put in large motors, doesn't matter. So you can get this fantastic torques applicable on it without worrying about the rest of the structure. And then that's why you can get this speed. In fact, that is running slow. So I've seen this machine, if you get your chocolates out of, if you buy Lind chocolates, and they're manufactured in Aachen. There's a very largest Lind factory is there. So this one packs chocolate there and it's a blur. So the speed is limited completely by the suction cup speed. And how quickly can you suck it and place it. So it's a blur. I mean, this thing moves just in the air, you can't see it literally, the end of it. And it is correct and accurate. And so idea is that there's a chocolate which comes on a line, it picks it up and places it, like in a Ferrero Rocher or something. It just places it in 6 different places. So it just acts like a blur, it's so fast. Now this one is IIT Delhi BTech project, the last one that you saw. Okay. And so only thing was that when they made it, it was very noisy. So unfortunately that semester it was done by Group Supervisor Professor Saha. But anyway, so that semester, that year I was in a sabbatical, so we not run the robotics course. So what they had done is, the cardinal sin is that they were doing point-to-point positioning. So it would start, stop, start, stop. So very noisy, continuously. So they were doing start, stop, because they had done a point-to-point positioning instead of doing a Jacobian control on a rate thing. But it was a good project. It's still around. A couple of more. So the idea is that if you want a very large torque, a very large force, aircraft simulators, vehicle simulators, this kind of very rapid pick and place options. So there's a whole class of parallel manipulators which are available, and we will take a sneak peek at them. Okay, we will do some analysis of it, okay, over 1 or 2 lectures, so that we understand what they are. We will not focus too much on them because it's a very advanced subject. I mean, the dynamics is more complicated. The kinematics is, well, the forward kinematics is very complicated. Inverse kinematics is extremely simple. Okay, so we will look at these. and then we will see where we go. Okay.
Serial robot, the
Yeah.
amount of weight that the robot can actually pick is very small compared
It's
to
very small,
weight
very
of the
small.
robot
The
itself.
KUKA you saw is a 5 kilo robot, that huge, tough beast. Well, it can pick more, but basically it's also based on a pick capability and a speed. It's a combination. So at its rated speed, it can pick something like 5 kilograms. That and that looks very strong. So on the other hand, with the parallel robot, usually the weight is split into 6 actuators. In this case, in the other one, then delta into 3 actuators. So it becomes much better. And there are some other nice things. The delta you saw is a constant orientation robot. So the orientation does not flip around, it just stays flat. So that's very useful for some pick and place applications. If you're picking from a table, placing it somewhere else, having a guarantee that it will not move around saves you quite a bit. Unless you want to have that ability to move it around. So for the example that you saw, what they have done is they have based a delta and then just put in a wrist at the end of the delta. So it was carrying those 3 motors around. But then you saw the motors at the base were this size. So very powerful. So the motors at the base were roughly the same size as the motors which you have at the base of the KUKA. So very strong, very agile, and so that's the whole idea. So if you typical application, aircraft simulators, vehicle simulators, lot of medical robotics is based on that, because you don't want very large manipulation. You don't want to move very large distances if you want to drill in a local area. So that's what is done. So you have a robot with all the motors sitting here, and then you put a patient in there, and then you make some accurate cuts. So typical application areas. Okay. So we'll stop here today.